Hello everyone, welcome to this lecture. Just to recap, in the last lecture we have discussed rigorously the notion of CCA security in the context of public key encryption schemes. So, the plan for this lecture is as follows. We will introduce the notion of CCA security for public key crypto systems. We will discuss the motivation for studying CCA security considering real world scenarios. We will see the formal definition of CCA security. Then we will see the CCA security definitions for key encapsulation mechanism, and then we will see a generic construction of CCA secure public key cipher from any CCA secure key encapsulation mechanism and any CCA secure symmetric key cipher. So, let us begin our discussion with the difference between the passive adversarial model and active adversarial model in the context of public key setting. So, if we consider the passive adversarial model, then the scenario is the following. So, imagine we have a receiver here who has done the key generation and he has set up its public key, made it available in the public domain, and we assume that its public key, namely the authenticated copy of the receiver's public key, is available in the public domain, and using it, say a sender encrypts a sequence of messages, say M1 to ML, and the resultant ciphertext are communicated over the channel. Then in the passive model, we assume that the adversary has the capability to only read the ciphertext. It cannot change the ciphertext contents, it cannot change their ordering, it cannot introduce new ciphertext and so on. Whereas if we go in the active adversarial model, then the adversary is more powerful in the sense it can not only read the ciphertext, but it can change the ciphertext contents, it can insert new ciphertext on its behalf, or pretending that as if they are coming from the sender. It can delete the ciphertext which were communicated by the sender, it can reorder the ciphertext, and it can do any kind of attack which you can think of, right. So, it is a more powerful adversarial model compared to the passive adversarial model. And it turns out, so just to recall, we have seen the difference between the passive adversarial model and the active adversarial model in the context of symmetric key setting. So, right now we are now doing the same discussion in the context of public key setting, and it turns out that compared to the private key setting, malicious or active adversaries are more of a concern in the public key setting. And this is because of the fact that in the public key setting, anyone can compute or communicate with a receiver just by accessing receiver's public key, because in the public key setting the encryption happens using the public key of the receiver, and since it will be available in the public domain, if I have an adversary and I want to compute ciphertext and send it to the receiver, I can do that. This is in contrast to the private key setting, where if I am an adversary and I do not have the symmetric key which is available between the sender and the receiver, then it is very unlikely for me to come up with a valid ciphertext and send it to the receiver on the behalf of the sender, if I am using an authenticated encryption scheme. So, that means malicious adversaries are really more of a concern in the public key setting compared to the private key setting. So, that motivates us to study CCA attacks in the context of public key world. So, what we are going to do next is we are going to see some real world scenarios where indeed CCA attacks can be launched. So, consider this example where, say, a password is shared between a user and a bank, and the bank's public key, bank's key public key is PK and its secret key is SK, and its public key PK is available in the public domain. And the usual protocol between a legitimate user and a bank is as follows. So, if a user wants to initiate a session with the bank, then the first thing the user does is it encrypts its password using the public key of the bank using some public key encryption process, and a resultant ciphertext is communicated over the channel. And on receiving the encrypted password, the bank decrypts the encrypted password and compares it with the password that it has stored with itself, and it gives an error message, namely incorrect password, if it finds that on decryption the recovered password, namely little m, is not the same as the password PWD which is stored at the bank's end. So, this is a standard protocol. So, now let us see what happens if we take this simple protocol in the malicious adversarial model. So, imagine we are given an adversary who is an active adversary and who has eavesdropped upon the encrypted password C. It knows the public key of the bank because it is available in the public domain, but the adversary is not aware of the password which is encrypted in the ciphertext C, and its goal is to find out what exactly is the password. Now, what the adversary can do is, since it knows what it can do is basically it can take the ciphertext C which has been communicated by encrypted password which has been communicated by a legitimate user to the bank, and it interrupts the communication, and what it does it modifies certain bits of the ciphertext C and come up with a new ciphertext C dash by encrypting some message M dash itself using the public key of the bank. So, what it is doing is it just stops the communication between the legitimate user and the bank, and instead it comes up with a new ciphertext, say C dash, and C dash is an encryption of some known plain text M dash which is given to the which is known already to the adversary, and or maybe we can imagine that in this particular example the adversary can even do nasty things. In fact, it can so happen that adversary do not know M dash and it just modifies certain bits of the ciphertext C and comes up with C dash, and it might be the case that C dash is an encryption of M dash, that is also possibility. So, whatever may be the case, the adversary forwards the ciphertext C dash to the bank and wait for the response of the bank. Now, if it sees that in the response to C dash on decrypting C dash the bank throws out the error message incorrect password, then basically adversary here is actually coming to know that M dash is not the right password which was encrypted in C, because if indeed M dash would have been the right password, right, which is encrypted in the ciphertext C, then on decrypting ciphertext C dash bank would not have thrown the error message incorrect password. But since the bank is throwing the message incorrect password, somehow the adversary here getting to learn that the password which is shared between the legitimate user and the bank is not M dash, it is something different from M dash. And now the adversary can try to repeat the same attack again. That means what it can do is it can just come up with another ciphertext, say C double dash, which could be an encryption of some plain text, say M double dash, and hope that indeed M double dash is the right password, and forwards the ciphertext C double dash to the bank and wait to see the bank's response. And again, if the error message comes, then the adversary learns here that the password is not M double dash and so on. So, what is happening here basically in this example is that adversary is somehow getting a decryption oracle service from the bank without actually letting the bank know that it is adversary who is actually persuading the bank to decrypt ciphertext of adversary's choice. Now, let us consider another application here, and here in this application, say we have a receiver Bob who has set up its public key and secret key, and the public key is available in the public domain, and say Alice has a email say M which it wants to communicate secretly to Bob. So, what it does is it runs the public key encryption algorithm using the public key of Bob, and the resultant encrypted mail C is communicated to Bob. Now, suppose Charlie is interested to find out what is happening, what exactly are the contents of the email. So, what Charlie can do it can eavesdrop the encrypted email, and what it can do it can modify certain bits of C to produce a new encrypted mail, say C dash, and send it to Bob and pretend as if that is an encrypted mail which Charlie would like to send to Bob, right. Now, Bob what it is going to do is when it receives the ciphertext C dash, it will think as if Charlie wants to send an encrypted mail to Bob, and on decryption what Bob can do is probably suppose on decrypting C dash it recovers the email content M dash, and it might be possible that Bob would like to reply back to Charlie, and while replying back it might want to quote the message or the email which Bob has obtained after decrypting the encrypted email C dash. That means the email reply which now Bob is sending might be concatenated with M dash depending upon the underlying application. Now, when this response from Bob along with the decrypted email m dash comes back to Charlie. What basically Charlie is getting here is it is getting decryption oracle service, namely it learns that the modified ciphertext C dash actually encrypts the email content m dash. And in this case actually if indeed my encryption process would have been secure, CCA secure, then this should not be possible, right. But since my encryption process is not CCA secure here, Bob here on receiving a modified ciphertext C dash, it is completely clueless that the modified email has been forwarded by an adversary here, and it is simply decrypting that modified ciphertext and responding back to the adversary, thinking that the email originated from the adversary. Now, let us see the final example here, and this is you can imagine a bidding protocol here, and the scenario is the following. We have an auctioneer who has its public key setup available in the public domain, and say we have two bidders who are bidding for a valuable object, and say the bidder Bob goes first. It has a private bit little m which it encrypts using the public key of the auctioneers, with the auctioneer in this case is Alice here. And now assume that a Charlie is a malicious bidder who wants to win the bid, but it does not know the bid value little m because that is encrypted using the public key of the Alice. So, what Charlie can do here is it can eavesdrop upon the encrypted bid of Bob, and after doing that it can modify the encrypted bid C to another bit C dash, and suppose my encryption process is such that the modified encrypted bit C dash is an encryption of the bit 2 times the bid of Bob, and forwards the modified encrypted bit C dash to Alice, and Charlie pretend as if C dash is the bid which Charlie would like to make here. So, this property here where it is possible for an adversary, namely a malicious Charlie, to eavesdrop a ciphertext of an unknown message, and from that ciphertext produce another related ciphertext C dash, which is an encryption of some related message, namely 2 times the message m which was encrypted in the ciphertext C, is called as the malleability property of ciphertext. So, recall we had when we were discussing symmetric encryption process, there also we discussed the notion of malleability, and malleability could be possible even in the context of public key encryption process. So, now in this example, if indeed it is possible for Charlie to convert C to C dash such that C dash is a public key encryption of the message 2 times m, then what Alice might do is when she decrypts C and C dash, she will find that C dash is the winning bit because it corresponds to the value 2 times m, and she can now publicly announce that Charlie has won the bid by bidding for the bid value 2 times m. And in this case, after learning the result, Charlie ends up getting a decryption oracle service from Alice and ends up winning the auction, which should have been avoided if indeed my encryption process would have been CCA secure. Right. So, now we have seen several real world scenarios where CCA attacks can be launched, where the adversary can get the decryption oracle service. So, hence now we have to study formally the notion of CCA security in the context of public key crypto system. So, let us formally define that. So, on a very high level, the goal of CCA security is to achieve indistinguishable encryptions even in the presence of decryption oracle and the knowledge of public key being available with the adversary. And this is modeled by a challenge response game. The rules of the game are as follows. The challenger runs the key generation algorithm, gives the public key to the adversary who is computationally bounded. So, since the public key is given explicitly to the adversary, it can get encryption oracle service on its own by encrypting any plain text of its choice. Now, what it can do in this experiment is it can ask for the decryption oracle service by submitting several ciphertext from the ciphertext base, and in response the challenger has to decrypt back all those ciphertext using the secret key SK, which is not known to the adversary. Now, the challenge phase starts where the adversary submits a pair of plain text, with the only restriction being that their length should be same. And to prepare the challenge ciphertext, our challenger randomly picks one of those messages and encrypts it using the public key PK. And now we give the adversary access to the post challenge decryption oracle service, where again it can ask for decryption oracle service or decryption for a mini ciphertext of his choice, with the only restriction being that this post challenge decryption oracle service is restricted from being the adversary is restricted to ask for the decryption of the challenge ciphertext C star, because if we do not put this restriction, then we cannot achieve any meaningful notion of secrecy. And if you look the 3 motivating examples that I given earlier, in all those 3 examples, the goal of the Charlie or the bad guy was to get the decryption oracle service of a modified ciphertext, but not for the ciphertext which it is interested to crack. Now, once the adversary gets the decryption oracle service for the post challenge decryption oracle queries, the adversary's goal is to identify whether C star is an encryption of M0 or M1. So, it submits its response or output, and the rule of the experiment is we say that the adversary has won the experiment, which equivalent to saying that the output of the experiment is 1 if and only if B dash is equal to B. That means, adversary has correctly identified what is encrypted in challenge ciphertext, and our security definition is we say that our encryption process is single message CCA secure if for every polytime adversary the success probability of adversary winning the game is upper bounded by some half plus negligible function in the security parameter, or equivalently the distinguishing advantage of the adversary is upper bounded by some negligible function. Namely, it does not matter whether C star is an encryption of M0 or M1, with almost same probability the response of the adversary will be same. The reason we are calling this definition as single message CCA secure, because adversary has just submitted a pair of challenge plain text and is seeing an encryption of one of them. We can extend this definition in a straightforward fashion or in a natural way to incorporate multi-message CCA security. The rules of the game will be almost same as for the single message CCA security, where challenger throws the public key to the adversary, adversary gets decryption oracle service, and now in the challenge phase it is allowed to submit a pair of vector of messages, with the only restriction being that component wise the message in the 0th vector and the message in the 1st vector should be of same length. To prepare the challenge ciphertext, the challenger picks one of these 2 vectors with equal probability for encryption, and then encrypts all the message plain text on those in the selected vector, and the challenge ciphertext vector is given to the adversary. The adversary again is now allowed to have access to the post challenge decryption oracle service, with the only restriction that it cannot ask for the decryption of any ciphertext which is present in the challenge ciphertext vector. Now, once adversary is sufficiently trained, it has to identify whether the challenge ciphertext vector it has seen corresponds to an encryption of the 0th vector or the 1st vector, and we say that the adversary has won the experiment or the output of the experiment is 1 if and only if it has correctly identified whether it is M0 or whether it is M1 which is encrypted in the challenge ciphertext vector C star. And our security definition is we say that our encryption process is multi-message CCA secure if for any polytime adversary participating in this experiment the probability that it can win the experiment is upper bounded by half plus some negligible function in the security parameter, or equivalently the distinguishing advantage of the adversary is upper bounded by some negligible function in the security parameter. And as expected, we can prove that single message CCA security and multi-message CCA security are equivalent even in the context of public key encryption schemes. So, I am not giving the full proof here, you can refer to the book by Katz-Lindell for the full proof. So, now let us define the notion of CCA security in the context of hybrid public key ciphers. So, remember in the last lecture we have discussed that how using a key encapsulation mechanism and a symmetric key encryption scheme we can come up with a combination of both of them to come up with a more efficient hybrid encryption process, right, where the key generation algorithm of the hybrid encryption process will run the key generation algorithm of the KEM and output the public key and secret key, where secret key will be available with the receiver and public key will be available in the public domain. The encryption process of the hybrid scheme will be as follows. It runs first a key encapsulation algorithm and obtains a symmetric key little k and an encapsulation of the key denoted by little c, and then the key little k is used to encrypt the plain text according to the symmetric key encryption algorithm to produce the ciphertext C dash, and the overall ciphertext is the encapsulation of the symmetric key and the encapsulation of the plain text. And analogously, the decryption happens at the receiving end. The receiver first decapsulate the encapsulation C and obtains the symmetric key little k, and once it obtains the symmetric key little k, it decapsulates the ciphertext component C dash to recover back the plain text little m using the decryption algorithm of the symmetric key encryption process. And also to recall, in the last lecture we have proved that if my KEM is CPA secure and my symmetric key encryption process is COA secure, then the overall scheme is CPA secure. But since now we are considering CCA security, we have to identify what should be the security properties of my underlying building blocks. It turns out that if I want to achieve CCA security, then definitely my underlying symmetric key encryption process in the hybrid encryption scheme should be CCA secure. It is not suffice to just have COA security or CPA security for the underlying symmetric key encryption process. To demonstrate my point, let us instantiate the underlying symmetric key block here in this hybrid encryption process by a counter mode of operation, which we know is CPA secure but not CCA secure. So, imagine that a sender has encrypted a message consisting of two blocks of all zeros using the hybrid encryption scheme as per the above hybrid encryption process, and the resultant ciphertext is C comma C dash, and as per the details of the encryption process of this hybrid encryption scheme, the way C comma C dash would have been produced is as follows. First, an encapsulation algorithm would have been executed to obtain a symmetric key and the encapsulation of that key, and then using the key k by invoking the counter mode of operation, the message block all zeros followed by all zeros would have been executed. So, the encryption of the message little m using the key as per the counter mode of operation will be as follows. A random counter will be selected, which will be available as part of the ciphertext component C dash, and the actual encryption of the blocks of the message will be C1 dash and C2 dash as per this counter mode of operation. Now, what we are going to see here in this example is that imagine there is an adversary who has eavesdropped the ciphertext C comma C dash, and imagine that adversary is an active adversary. Then by observing C comma C dash, it is very easy for that adversary to produce a modified ciphertext C comma C double dash, such that when this modified ciphertext is forwarded to the receiver and decrypted as per this hybrid encryption process, it leads to the plain text all ones followed by all zeros. And the way adversary can do that is by exploiting the malleability of the counter mode of operation. Basically, he has to produce C double dash, where the counter value, namely C0 dash, is retained as it is, and the C2 dash component of the ciphertext C dash is also retained as it is. The modification is only in the ciphertext component C1 dash. C1 dash is now changed to C1 double dash as follows, and if C1 dash is changed to C1 double dash as follows, then the effect of all zeros and all zeros cancels out, and basically C1 double dash now corresponds to a counter mode of operation for the message block all ones. And now since this overall process is malleable, we can easily show that this is not going to be CCA secure. So, that means if at all we want the overall hybrid encryption process to be CCA secure, definitely my underlying symmetric key encryption scheme which I am using should be CCA secure. But it turns out that just instantiating the underlying symmetric key encryption by a CCA secure symmetric key encryption does not suffice to give us an overall CCA secure hybrid encryption process. And the reason for this is, if we play the CCA game against this hybrid encryption process, then remember that in the CCA game adversary is given access to the decryption oracle service. Namely, the adversary can now make decryption oracle service for any kind of modified ciphertext, where the first part of the ciphertext can be any C star, namely any encapsulation followed by anything. And to respond to those modified queries, modified decryption oracle queries, the challenger has to basically decrypt such modified ciphertext using the secret key SK. Now, if you see the decryption algorithm of this hybrid encryption scheme, any decryption oracle's query of the form C star followed by anything, when it gets decrypted by the challenger in the CCA game, Basically, it provides implicitly the adversary oracle access to the decapsulation oracle service under the unknown secret key Sk, because on decrypting the modified ciphertext, adversary will come to learn what exactly the decapsulation of C star under the unknown secret key Sk corresponds to. That means, we now need a CCA secure instantiation of the key encapsulation mechanism as well, to hope that the overall hybrid encryption process results in a CCA secure public key encryption process. So, let us first define the notion of CCA security for key encapsulation mechanism, and on a very high level the goal of a CCA secure key encapsulation mechanism should be is to ensure the following. So, imagine we have a receiver who runs the key generation algorithm of a CCA secure encapsulation mechanism and set up the public key, and say a sender is there which runs the key encapsulation algorithm of that scheme, obtains a secret key Sk and the encapsulation of the key little c, and the encapsulation is sent to the receiver, and say there is a malicious adversary who has eavesdropped the encapsulation c, and now imagine that my adversary gets the decapsulation oracle service for any encapsulation c dash different from c. Now, by getting polynomial number of decapsulation oracle service, we require that my adversary from the viewpoint of my adversary, the encapsulation C which it has seen earlier should be still independent of the key K which is encapsulated in this C, right. So, the advantage here that my adversary is now getting is that it is now getting explicit decapsulation oracle service, which we have now to model in our experiment. So, to model the above requirement, the experiment is as follows. Our challenger, it runs the key generation algorithm, and using the public key it runs the encapsulation algorithm to obtain a pair C comma K, and now it prepares the challenge for the adversary as follows. It tosses a fair coin. If the coin toss is 0, then it picks a random element K hat from the key space, whereas if the coin toss is 1, then the element K hat is the key K which is actually encapsulated in the encapsulation C, and the challenge for the adversary is as follows. The public key is given, the encapsulation C is given, and K hat is given, and the goal of the adversary is to identify whether K dash is a random element from the key space, namely whether B is equal to 0, or whether K dash is the same key which is encapsulated in C, namely B equal to 1. But now we model the decapsulation oracle service by allowing the adversary to ask for decapsulation of any encapsulation of its choice, with the only restriction being that this decapsulation oracle service should not be for the encapsulation C, they should be different from C. And the adversary is allowed to adaptively submit its query, and in response to the decapsulation oracle queries, the challenger responds by decapsulating all those queries under the unknown secret key Sk which is not known to the adversary, and after making polynomial number of queries, the adversary now has to identify and solve its challenge, namely it has to identify whether he has seen a challenge as per method little b equal to 0 or as per the method little b equal to 1. And the definition of the experiment is, we say that the adversary has won the experiment, which we denote by saying that the output of the experiment is 1 if and only if adversary has ensured b dash equal to b. And we say that our key encapsulation mechanism is CCA secure if for every polytime adversary there exists some negligible function such that the probability of that adversary winning the experiment is upper bounded by half plus negligible function, or equivalently the distinguishing advantage of that adversary is upper bounded by some negligible function in the security parameter. So, now we are going to see that if we are given a CCA secure chem and a CCA secure symmetric key cipher, then if we combine it we get a CCA secure asymmetric key cipher. So, imagine we are given a CCA secure chem and a CCA secure symmetric key encryption process, then we can combine it in the same way as we have done to obtain a CPA secure asymmetric key cipher in the last lecture. So, my key generation algorithm of the hybrid encryption process will be simply the key generation algorithm of the key encapsulation mechanism. To encrypt a plain text using the public key PK, what sender is going to do is it will run the encapsulation algorithm and will obtain a key k and its encapsulation C, and using the key k it will invoke the encryption algorithm of the underlying symmetric encryption process to encrypt the plain text little m and obtain its encapsulation C dash, and the overall ciphertext will be C comma C dash. On the other hand, the receiver who possesses the secret key Sk, on receiving the ciphertext C comma C dash will first decapsulate the C part of the ciphertext to retrieve the encapsulated key little k, and then that little k then the key little k is used to decapsulate the C dash component of the ciphertext as per the decryption algorithm of the symmetric encryption process to get back the actual plain text little m. And we can prove that if my key encapsulation mechanism is CCA secure as per the definition that we have just given, and if my underlying symmetric key encryption process is CCA secure, then this generic way of combining these two primitives is going to give us a public key encryption process which is CCA secure. And the proof again will be something similar to the hybrid argument style proof which we had given in the last lecture to prove the CPA security of the generic construction of the hybrid scheme that we had discussed in that lecture. So, I am leaving the full formal details of the proof to you as an exercise. So, that brings me to the end of this lecture. Just to summarize, in this lecture we introduced the notion of CCA security in the context of public key encryption scheme. We have seen the malleability, what exactly malleability of public key encryption schemes means, and we have seen the definition of CCA security for key encapsulation mechanism and discussed that if we are given a CCA secure key encapsulation mechanism and a CCA secure symmetric key cipher, then we can combine them generically to obtain a hybrid encryption process which is public key hybrid encryption process and CCA secure. Thank you.